We'll start recording. So I see the file titled pho underscore hv3.pdf. Is that the file?
Okay, so Leon says he didn't replace anything.
I read that. But I bet I saw your attempt at the swimming pool question. Did I miss anything?
He says it's called swimming pool.
Okay, where did you submit it? Maybe I'm looking at the wrong place.
Under notes.
Under notes. Yeah, but no, I'm still getting to that same hole. So just to be clear, you made two submissions, right? First the swimming pool and then this. Yeah, somehow I can only see the later submission.
You can upload it as a file to the Zoom thing, to the Zoom chat, maybe.
No, that's fine. So let me maybe just repeat the hint I offered last time. So let me just bring up the last lecture note. Okay, so this is from last time. So we got to this integral. Right here. All right. Alpha is the speed ratio that we're trying to maximize for whatever strategy, right? So we basically have like two questions in one here. The ultimate task is to maximize alpha, but the way we get there is first we find the omega of r, the function omega of r that describes the trajectory of the student such that alpha is maximum. Okay, so we find omega of r, then plug it back into this integral, do the integral, and solve for alpha. So alpha now shows up in two places, in the upper limit of integration and inside the integral. So the idea is, and these guys are all dimensionful, except for alpha. Alpha is the ratio, but omega is the actual angular speed, and r is the radius, v is the speed. They all have units. So what you want to do every time you deal with expressions like this. Oh, thank you. I'll bring it up. Every time you deal with an expression like this, you want to do some substitutions so as to minimize the number of independent variables or parameters showing up. Okay, it's a good habit for whatever purposes. It may be just for the sake of integration, or just to simplify life and see what the important combos are. So last time I told you to try to redefine variables, like switch to dimensionless variables so that alpha disappears from the inside of the integral.
So
Okay.
Alvin just uploaded the swimming pool solution to the Zoom chat.
Yeah, it was downloading and it's probably done now. Okay, here we go. So let me stop sharing mine. Share his. Yeah, so you try to do variation right from the start. So those of you who are not familiar with variational calculus, you consider some perturbed function in the form of the original function omega of r plus some perturbation epsilon times eta. Eta is another function that satisfies some boundary conditions. And then you just basically kind of expand the integral, the functional, in terms of epsilon and eta. So it probably will get you to the right place. But I'm not seeing the right combos at the end. So I suspect you may have confused the sign at some point, because the answer for omega is actually extremely simple. So let me first explain why I want you to do the massaging, because that will allow you to avoid this heavy artillery of variational calculus altogether. So if alpha only shows up in the upper limit of the integral, and omega does not show up in terms of derivatives of it, right? It's just the function itself. So normally when you have a functional, it depends on like omega, it depends on omega, like first, second, and whatever derivatives of omega, okay? That's when you really need Euler-Lagrange equations. But there are no derivatives of omega, just omega itself. And if alpha is not present inside the integral, that just makes things so much simpler. So why? Just think about it conceptually. What would maximize alpha? If you could minimize the integrand, and again, integrand does not depend on alpha. So if you minimize it just by playing with omega, that will imply that for the fixed value of pi, you would need to integrate over a longer interval. Okay? And that's exactly maximizing the alpha, because alpha tells you the length of the interval. Are you guys with me on this? Okay, so that means this task of maximizing alpha is equivalent to the task of minimizing the integrand with respect to omega. You vary omega, try to see which one minimizes the integrand. Now, again, it's conceptually may not be super intuitive because omega is a function. How do you do that? But just treat it as a variable. So basically, it's a function of r, but treat it as a variable. So the idea is that for every r, like a fixed value of r, you want to find such an omega that gives the minimum value for this fraction. And this is a fairly simple task. So basically, you forget that r was a variable. You think omega is the new variable, and minimize this function. So you minimize this combo with respect to omega. This is just a straightforward calculus exercise. But don't do it yet. Like first simplify the integral, because alpha actually is hiding in here. So you want to like massage this expression, switch to a unitless omega, okay? And once you do that, minimize with respect to that unitless omega. And that will give you some omega, okay? Some equation on omega, and then you can solve it and get omega, but it's actually not required. You could just use that to plug it back into the integral, compute the integral, and you'll get some equation on alpha. And I believe I warned you, that equation will be transcendental. There won't be like an explicit solution to that equation, but numerically you could solve it using some graphing calculator or packages like Mathematica or Maple. Okay, so the approximate numerical answer for alpha is 4.6. So this is actually better than pi plus 1, right? Pi plus 1 was 4.14, and this is 4.6. Okay, folks, do you have any questions? Yeah, I still want you to try this because you'll enjoy getting it. Yeah, but once again, and the important thing is to get that integral to the simplest possible form. Did you have any questions about the upcoming homework problem? There were like 6 problems. Is everything clear? Do you know what to do in every problem? Any questions at all? Okay, so Sunday night is the hard deadline on that, okay? And folks, I'm just thinking, so if you get stuck on some part of the problem, you could start a discussion in the Google group. Of course, you can talk to each other, that's fine. But I thought if you start a discussion, I'd also see that. So either your classmates or myself could respond to that. So this is a better place to post your questions, okay? Okay, then let's start a new topic. In fact, our problems are not catching up to the topics yet, but these are all good problems. Okay, I was thinking about doing non-inertial system, non-inertial frames, so that we can revisit some older problems and also learn some new fun stuff. So, non-inertial frames. Yeah, the basic idea is that, yeah, we know that if our reference frame is accelerating with respect to some other frame, laws of physics don't have to be the same in the two frames. Yeah, so the two frames have, say, common x-axis and parallel y-axis. So I can label them all. So this is x prime, y prime, and this is x, y, and the orange frame is accelerating with respect to the purple frame with some acceleration a. Okay. So a is the relative acceleration. So technically, you know what to do in terms of kinematics, right? You know how to relate accelerations and so and such. But what we really want to understand is how to handle forces, because forces are the things that usually people mean by laws of physics. So what happens is something actually pretty interesting. So Newton found effects. If you have an object that's being observed from two frames, then let's say there are no forces in the xy frame. So, but there is a fictitious force in the prime frame. Okay, so no forces in the xy frame. Fictitious force in the x prime y prime frame. We call this forces of inertia. So some of it we already discussed. So if you're driving in a car and let's say you speed up, you feel that you're being pushed back, right? But there is no real force acting on you. You cannot present an object or an agent or a field that actually pushes you. So that's how we know it's a fake force. In a rotating reference frame, we already discussed that. Say if you put a bowling ball on a merry-go-round, it wants to roll off. Again, there is this fake force, centrifugal force. So in general, we need to understand two things: the magnitude and direction of such a fake force. And things turn to be actually quite easy. So first off, the direction of the, like, which way do you think the direction of the force is? Just think that the orange frame is accelerating car. Which way do you feel the force? What's that?
Opposite A.
Exactly. So this is opposite. Force of inertia is anti-parallel to A. Now, how large is it? Well, it turns out that basically, since every object in this frame experienced the same exact acceleration, equal and opposite to the acceleration of the frame with respect to ground, that means the force should be just proportional to mass times acceleration. Okay? So F inertia equals negative ma. So this is how you find the force of inertia. With this extra fictitious force, you can do Newton's second law in non-inertial frames. Non-inertial frame. Just add that force to the mix, and that's it. Okay? Now, a conceptually important remark here. You see, for every object, the force is just proportional to the mass of that object. What other force has the same feature?
The centripetal.
I'm talking about like a physical force, right? Centripetal is not a specific interaction, right? Every time it's some other, like it's some specific force that plays that role, or maybe a mix of forces that play that role. But out of the like handful of forces that we learned with you guys, or you learned, which force has behaves the same way? That is, it's proportional to the mass of the object.
Like, can I guess like Coriolis?
Well,
Because
Coriolis is a force of inertia, so it's a partial case of this.
yeah, it is. So
But
like,
out of the real forces, right?
oh yeah,
Very first force we actually started. Let me check what's in the chat. Not really. So once again, it's it looks like some fixed acceleration times the mass of the object. Friction doesn't really do that.
oh, gravity.
Yes, gravity, exactly, gravity. Very similar to force of gravity. Which is just mg, right? So minus a looks like my minus a is effectively the analog of g. Okay, so you can't imagine how profound consequences this had. So did we guys discuss Einstein elevator and the Coulomb's principle with you at all? Maybe in the spring we did, didn't we? But not recently. Okay, so like this simple observation led Einstein to state the Coulomb principle and like paved the way to general theory of relativity. Well, it wasn't just Einstein. Mach did a lot of conceptual work there as well. But so let me remind you how that works. So what is an Einstein's elevator? Basically, elevator somewhere in outer space. And you put the person here. And first, this could be a regular elevator in like a regular building. Yeah. So, and again, I have to ask you, we did discuss the concept of apparent weight with you in the spring, right? So apparent weight is what you feel, right? So when the elevator starts going up, for the very first moment, you feel heavy. When it starts going down, for the very first moment, you feel light. When you drive in a car over the top of a hill, you feel light as well. And if you drive in a car like on the bottom of a trough, you feel heavy. So why is that? Well, because that's an accelerative reference frame. There is an extra force of inertia that alters how you feel. But the way to interpret it is to understand what makes you feel. Gravity, believe it or not, we humans cannot really feel gravity. Think about it. If the only force acting on you is gravity, you don't feel it. Don't do that at home, but like, what is a typical situation when the only force acting on you is gravity? Free fall. Yes, Joseph?
Skydiving.
Sorry, can you repeat that?
Skydiving.
Yeah, so when you're free falling, like technically, you do feel something, but that's because you're not a point particle. Have you jumped from like a tall enough stand in a swimming pool? Has anybody? So yeah, I did from like a 5-meter stand, and it literally lasts a second, as you know, from kinematics. But it feels like forever, and you do feel something. Okay, but that's because you're not a point particle. Like your stomach moves with respect to the rest of your body, and you feel that. But if you're really a point particle, you don't feel it. Say astronauts, right? They feel weightless. This is extreme. But the force of gravity on them is not zero. It is weaker than that on Earth, but not so much weaker. It's probably maybe just 20% less than typical. But they feel weightless. Why? Because they're free falling, right? They're only subject to gravity. They're making circular orbit just because it's actually circular motion, and force of gravity is the centrifugal force here. But it is the only force, and they don't feel it. Yeah, so when you do skydiving, you don't feel any forces. Is that convincing enough that we actually don't feel force of gravity? And that was the first signal to Einstein to think of gravity as not a force, but a feature of space-time, curvature of space-time to be precise. But let's get back to this elevator. So what makes us feel weight? It's actually some other forces, in particular normal force. Normal force is what makes you feel. So normal force is basically causing apparent weight. And if it gets larger, you feel heavier, and if it gets less, we feel lighter. Okay, so let's just do a quick exercise on Newton's second law. Let's say there is an upward acceleration of the elevator. Let's find the apparent weight of the person. We already know the person is going to feel heavier. So let's just do the actual calculation. So this is force of gravity, and this is normal force. We can write Newton's second law for the person. And let's say on the y-axis, choose the standard vertical up y-axis. So for the y projection of Newton's second law, we have plus n minus mg equals plus ma, right? And from here, we get that normal force equals mg plus a. So this extra a is what makes the person feel heavier. Now imagine that we're in outer space. So we take this elevator into outer space. Yeah, let's take a volunteer. Let's say it's Andrew. So Andrew was in an elevator in a regular building in New York. He felt this way, and now we would take it in outer space. Okay. The elevator doesn't have any windows, so he cannot look outside and figure out what's happening. So he can only feel some feelings, right? So what does it mean for us, taking elevator to outer space? That means basically putting G to 0. Far away from any planets or stars, there is no gravity. However, there is this part in here, the A part. So if we now set A equal G numerically, what does he feel? Feels MA, which is mg. So Andrew will feel normal. So Einstein's statement here is that there is no way for the person to tell the difference, whether that person is on Earth, standing still, or in outer space, being pushed up with acceleration A equal G. And you want to comment on this?
Oh, no, I don't know. It's just accidentally unmuted. Yeah.
Oh, okay. So now tell me, folks, what if somebody actually pushed the elevator down with the same acceleration? What would happen to Andrew?
Then he'd feel weightless or like lighter.
So well, let me actually draw that. Not sure if Andrew would appreciate that, but we'll do it anyway. So now you're being pushed, your elevator is being pushed with acceleration A downward. And again, numerically, we set A equal G. So how would things look like? So remember, it's outer space. Andrew is somewhere here, and we push the elevator down.
Then there's going to be a fictitious force upwards.
And how would, what should I draw? Like, how would Andrew look?
So the person would be like on top. Okay, so like I guess Andrew would feel like he's standing on his head.
Exactly. So from our perspective, it looks like he's just basically hitting the ceiling of the elevator with his head. But from his perspective, he would think that he's upside down, standing on his head. So Andrew would totally think that gravity is actually pointing up. Okay.
So am I going to hit my head against the ceiling?
You won't think of it as a ceiling. You would think it's a floor, and you're upside down.
Oh, so I'll just be doing a perfect headstand?
Yep.
Nice.
So you would feel that there is gravity that way. Okay. So you see, what we got like used to think of as gravity is actually totally artificial. We can imitate gravity. Of course, Joseph, no Andrews got hurt during this experiment. I have multiple copies of him here, so it's okay. What was I going to say? Yeah, so we can imitate gravity by considering accelerated frames. Okay, so this is the conclusion here. We can imitate force of gravity by using accelerated frames. And interestingly, a natural extension of this statement is that you can actually get rid of gravity, right? So if you can like imitate additional gravity, you can actually get rid of gravity. You can cancel gravity. But I have to be cautious here. I'm going to say locally. Because what happens is that force of gravity tends to get weaker as you go away from the gravitating body. Accelerated frame doesn't do that, right? This acceleration that gives rise to the force of inertia is constant everywhere, or it may not be constant anywhere. Let's say if we are considering a rotating frame with some fixed omega, we know that the acceleration is omega squared times r. So the farther away you are from the center of rotation, the greater the acceleration. If you go very far, it gets bigger and bigger and bigger. Gravity doesn't do that. Gravity gets weaker as you go away from whatever bodies. Am I making sense? So this is not a like 100% equivalence. It's a local equivalence within a small enough amount of space. Okay, that's all Einstein said. So locally, you can cancel gravity, you can imitate gravity, whatever you wish. So this is the equivalence principle, the foundational principle of general theory of relativity. Yes, Andrew. Again, when you get to consider very small distances, things blow up, and that's a totally separate discussion. Okay, but at least locally things work fine, and they can be considered equivalent. So let me just tell you what is like the ultimate state of the art on this. So let me just reiterate that statement. So laws of physics don't have to be the same in non-inertial frames. And what that means, maybe first counterintuitively, but it actually works out, is that at the fundamental level, if you have empty space in some frame, like empty means you have no particles there, okay? And then you switch to an accelerated frame. So you jump on an accelerated train. What you may start seeing is some artificial particles, some fictitious particles. Particles that don't exist in one frame may exist in another frame. So for that, you need to look into quantum field theory, okay? And the first person who did that, so let me actually put that down, because later on you may want to be interested in finding more about it. So say no particles in the laboratory frame, but you may have, yes, particles in accelerated frame. So the first person who did this was Bill Unruh. He's still alive. He is a professor at the University of Vancouver. And this is what we call the Unruh effect. Yeah, if you want to Google this, just Google Unruh effect. Now, there is another person who you know, who is no longer with us, unfortunately, that actually built on top of this. Any ideas?
So Leon said Feynman?
No, that was after Feynman, actually. Well, actually, Feynman could have been alive when Unruh came up with this, but well, maybe not the person of the same caliber, but certainly an interesting character. No, you're going
after.
back after, yes.
Is it Hawking?
Yep.
Ah.
So what am I talking about? I'm talking about black hole evaporation.
Oh, Hawking radiation?
Yes.
Is it that like particles appear out of nothing, and if they appear sufficiently close to a black hole, one of them will become a real particle and escape, and the other one will fall into the black hole? So black holes lose
What you
mass?
said is kind of Penrose's interpretation of the Hawking radiation. Yeah, Hawking's radiation is another name for this. So let me first focus on this, and then yeah, I'll comment on Andrew's statement. So So assuming the idea that accelerated frame is equivalent to some gravitational field locally, right? And vice versa, a gravitational field can be replaced by some accelerated frame, and then you apply Unruh effect to that. So Unruh derived it for like uniform acceleration, but of course you can generalize it to non-uniform acceleration. So if you think of a black hole that provides gravitational field around it, you can view that as a set of locally accelerated frames. And as such, you may expect some extra particles that don't exist in the laboratory frame. And those are the particles that actually eventually escape the black hole, and we perceive it as radiation, Hawking radiation. So Hawking derived that precisely using Unruh's approach, just applied it to the specific gravitational field of the black hole. So the math is brutal there. Basically, Hawking's genius there was that he was able to massage a tricky integral and get some digestible results from it. So if you check it out, it's a really neat mathematical trick that he did, and that allowed to get some meaningful results. Okay, but what Andrew was saying is basically Roger Penrose's, by the way, this year's Nobel Prize winner. That's his interpretation of Hawking radiation. It's funny that Penrose is actually a mathematician and Hawking is supposed to be a physicist. So, but they kind of switch roles in this. You know, they did a lot of things together. So what Penrose got Nobel Prize for is what they basically did together with Hawking. Hawking was alive, he would have also got the prize today, this year. So what do I mean by mathematician versus physicist? So math people, they usually say, oh, I don't care like what that means as long as it works. So you have some theory, you have a recipe to compute things. So you compute things, you predict some results, and then you do the experiment, you get, you get exactly the results you predicted. That means your theory is fine. You don't really care what that means, okay? And the physicists will say, oh, well, actually, you want to make sense out of what you're doing, right? The quantities you're dealing with, they must have some meaning, some meaningful interpretation. So surprisingly, as I said, in this framework, Hawking did not care, and Penrose did. So Penrose came up with that neat explanation that Andrew brought up. That, again, we'll probably revisit it at some point, but if you have a black hole and this is the event horizon, that means nothing can escape the black hole. But since you have a very strong gravitational field, that energy is enough to momentarily produce an electron-positron pair. As you know, positron is the electron antiparticle. So you have, say, positron just inside the horizon, and electron just outside the horizon. So positron falls into the black hole, an electron escapes. And we receive this electron, so we think, okay, we receive some radiation from the black hole. Now what happens? What happens is that black hole spends the energy equivalent to the two masses of these two particles, and one escaped. So basically, black hole just lost the amount of mass equivalent to the mass of one electron. Okay, so that's why we say a black hole has evaporated a little bit, right? It lost some small amount. So at least this kind of explains why black holes can, in principle, allow some kind of radiation to come out. So this was Penrose's explanation. Okay, welcome, Abhijit.
I don't have any questions. I just came from the doctor's appointment.
Yeah, is everything okay?
Yeah, I just got a test for corona. Yeah, that's all.
I see. Leon, what do you mean, doctor of philosophy? Trying to say we're doing philosophy here?
No, I think he's just joking about my Doctor Who point.
Gotcha. Yeah, it's a good one. Okay, so folks, any questions, comments, complaints? I do, yes. I didn't realize you were responding to that. Okay, so folks, you see, like sometimes a very simple idea, such as Einstein's elevator, like really like high school physics, if you push hard enough, well, you have to have a genius like Einstein and then later Unruh and Hawking, but it actually gets to some very important consequences, okay? So just trace the path from Einstein's elevator to Hawking radiation. Okay, so let's consider some examples, then we'll take a break and consider maybe some more problems. So I want to revisit that question. I'm trying to see, I think we did that problem, but let me just make sure everybody's on the same page. Remember that problem with two blocks on top of one another? You apply a force to the top block. Now, there is no friction between the bottom block and the floor, but there is some friction between the blocks. So the question, oh, you're given the masses. And the mu and g, of course, we want to find the minimum force that would make the top block slide across the bottom one. So remember, we solved it first straightforwardly by writing down the acceleration of the bottom block in the lab frame, acceleration of the top block with in the laboratory frame, and then just saying that the top acceleration must be greater than the bottom one. Then that would mean that it's actually sliding across. But you can do the same thing in the reference frame of the bottom block, which is not inertial. So in the frame of M2, frame of F2, what do you have? First off, all you need to say is that the force F net must be greater than 0. Okay. Now, what is F net? F net, let me put the vector here. F net on M1, right? F net on M1 must be greater than 0. So what is it? It's the sum of all forces acting on M1. So let's do some other forces here. Obviously, there is force of friction acting from M2 on M1. Yeah, no surprise here. But in addition to that, we need to include the force of inertia. Which way is it?
Down.
Down, like you mean down, down?
Well, isn't that what inertia is? Oh, up.
So how do we determine the force of inertia?
Oh, I wasn't here for this. Sorry.
Oh, okay. So yeah, just review. So the idea is very simple. Forces of inertia, the anti-parallel to the acceleration of the frame, right? If you speed up in a car, you're being pushed back. So the force is opposite to acceleration. Magnitude-wise, it's simply the mass of the object times that acceleration. So applying it to this picture, we know that this orange force of inertia, the fictitious force, is pointing to the left, and we should add them all up, okay? So first F applied plus friction plus F of inertia, but on the x-axis, assuming that x is to the right, we have F minus F inertia must be greater than 0. And in fact, minimum force would correspond to equality. And so F min minus F of inertia equals 0. Okay, so force of F min is then equal friction plus force of inertia. Friction is easy, right? It's mu m1g. Does that make sense? That's the normal force on m1. Now, force of inertia. We know that force of inertia equals negative m1 times a of 1 with respect to 2, or the acceleration of 2, right? All right. Maybe I should be careful here. Acceleration of 2, because we're in the frame of m2. Now, what is that acceleration? Any ideas how to quickly find that?
Well, would you just like switch back to the lab frame and then use like the friction for Newton's third law? Because you're still in the frame of block 2, then the acceleration of 2 is like 0, right? But then
okay, that reminds me of another thing that I wanted to discuss today, and that's what we'll do after the break. The black box trick. So there is no friction with the floor. So if you say that it's barely sliding, right? So they kind of still moving together as a whole. That means we can find their common acceleration simply by taking this net force, F, and divide it by the total mass. Because all those frictions you mentioned, right, between the blocks, they're the internal forces. If you like consider the total force, they cancel out. Okay, so A2 can simply be found as F divided by M1 plus M2. So we got plus F min M1 plus M2. So basically you have F min showing up in 2 places, but you do some math and you solve for it. Right? So what I will ask you to do during the break is to go back and check if that's the same answers we got using just the laboratory thing. You got 1 minus m times m2, right? m2 over 1 plus m2 equal mu m1g. Gives us f min equal mu m1g times m1 plus m2 over something is weird here. Yeah, but this should be. Did I miss anything, folks? It shouldn't be this simple. Should be M2 over M1.
Well, wouldn't the M1 just cancel?
Oh, wait a second. Why did I put M2 here? My bad. Yeah, they look like they shouldn't. That's exactly my concern. This is actually M1, right? This is M1. I'm not sure why I put M2.
Mhm.
You see, that's another evaluation trick. Let's pretend I did it on purpose. So when you get a suspicious answer, go back and check your work. So with this will become M2 over M1. The other way, no, the other way around. M1 over M2. You see that, folks? Okay. Now go back and check if this is the same answer as we got like a few weeks back when we just considered the laboratory effect. Okay. So let's take a break, maybe like, I don't know, 6 minutes, and then we'll talk about that other trick. Okay. Oh, okay. Thank you. That can spin. So you have a person. Andrew's already volunteered, so we'll use Abhijit here. So if you have a person that is pressed against the wall, have you seen this before? Some parks, amusement parks still have it. So the idea is that the person first standing on the floor and the cylinder starts spinning, and then it reaches a certain rate, after which the floor gets removed, but the people, they just pressed against the wall so they don't fall down. So one way to represent what's happening is to consider the lab frame. So in the lab frame, you have, well, you have force of gravity, of course, and you have friction from the wall going up, and you have the normal force from the wall going toward the center. And it's the normal force that, plays the role of centripetal force. So mg.
Wait, sorry, what's the force going upwards?
Friction between the wall and the person.
Oh, okay.
And this is the normal force. Now let me maybe just do it a little bit more explicitly. So first in the lab frame. In the lab frame, you have F net equal mg plus F plus N equal MA. And the idea that these two forces cancel each other, and the normal force plays the role of centripetal force. For example, you could ask yourself, okay, how fast do you need to spin the cylinder so that the person doesn't slide down? What do you need to know for that? Well, it kind of makes sense that you need to be given the coefficient of friction, because if the wall is very slippery, you need to spin it faster and vice versa. Of course, you need to know the G. Do you think the mass of the person is important? Do you think the radius of the cylinder is important?
That might be. I don't
Can
think
we
the
play
mass
with-
is important.
Okay. Remember how to answer all these questions right away without even thinking? By looking at the units, right? There are no kilograms and no mega. Mass is the only possible quantity that may have kilograms. So if we stick mass in the answer, there would be some uncancelled kilograms, which we can't have. So this simple logic tells you that mass is not going to matter. Unless you have two masses. If you have two masses, then it's a totally different story. They may show up in the answer as a ratio. But as long as there is only one relevant mass, it can't show up in the answer. Does that make sense? Okay. Now, as far as the radius, well, what's the units of omega? Let's play that game before we even do anything.
Radians over seconds.
Okay, or just 1/2, right? Because radian is a unitless thing. Units of mu are just 1, right? That's how we represent unitless things. Units of g, meters per second squared, and the units of r are meters. So do you see what you need, what kind of combo you would need to form to get the answer?
It's probably like r over g and the square root of that times mu.
Well, let's first try this. What do we get if we form this combo?
And we just get, oh, we get, no, it's g over r.
Yeah, so this is second, so we really need the inverse, okay? We need this. Now, let's answer this question. If we increase mu, mu is hard to catch because it's unitless, right? It can show up anywhere in whatever power. So let's use some other techniques such as physical sense. If we increase mu, would that imply a greater omega or smaller omega?
This mu is with the walls, right?
Right. So
Probably a
let's use
greater.
S.
I think a greater, like, because then the person will be experiencing more force, like holding onto him.
Exactly. So if mu increases, then omega may be lower, right? You don't need to spin it as fast, right?
Yeah.
And vice versa. If this is very slippery, you need to spin it faster. So where should mu be present in the answer? Somewhere on the bottom, right? But it may be on the root or maybe outside of the root. What does your intuition tell you? Well, let's try both, right? Or, and then we'll see what we get. Well, some of you may offer some exotic power, like 3/2 or whatever, but I wouldn't go that far. Okay, folks, look, we haven't done any physics or math yet. We just play with the units and we kind of narrow things down to 2 possible answers. Okay? So this is what I recommend you do. Like, train yourself to do it quickly. Then you want to do it in every single problem, really. Okay? Because it gives you a good idea what the answer should look like. Okay, but now let's switch back to the solution itself. So from the lamp frame perspective, we just have this, and the normal force plays the role of centripetal force. So the magnitude of N equals m times acceleration. Acceleration is the centripetal acceleration, which is omega squared times r, right? That's on one hand. On the other hand, we know that force of gravity cancels with friction. That means friction equals mg. Okay. On the other hand, how do we connect these two things? On the other hand, we know that friction is also equal mu times n. Does that make sense? So let's put it together. So we have mg equal mu times n, and n is this combo, m omega squared times r. M cancels as expected. And then you solve for omega, get square root of g over mu r. Okay, looks like this was the right idea. Okay. Okay, but now, how do things look if you do the same thing in non-inertial frame? So let me erase this unit analysis. And do this in non-inertial frame. So in the non-inertial, like the rotating frame, right? With omega. In non-inertial frame, what you have on the person, so in this frame, there is no acceleration, right? Because you switch to the frame, and in that frame, you have no acceleration. But how many forces do you have now? In addition to the 3 real forces, there is one fictitious force. So friction, gravity, normal, and here we go, F inertia, the centrifugal force. So if you were to write Newton's second law, you would say F net equals ma, but a is 0 now, and F net is the sum of 4 forces. F plus mg plus n plus F of inertia equals 0. And again, the y forces cancel each other out, and the x forces cancel each other out. But from the x equation, you get that normal force equals force of inertia by magnitude. And as you remember, the magnitude of force of inertia is given by the mass of the person times the acceleration of that frame, which is omega squared times r. So you basically get the same exact equation, but you have a totally different interpretation of what's happening. Okay, I'm not going to continue because the rest is identical to what we already did. Okay, folks, does this approach make sense? So again, math-wise, it's equivalent, but and this is exactly the fix, really. So this is the Newton's fix. You introduce this force of inertia, defined as negative ma, and everything works out the same way. But sometimes dealing with non-inertial frames is just simpler than sticking with the laboratory frame all the time. Okay. So let me also talk about Coriolis's force that I already mentioned. And then I'll assign you another sort of long-term problem to discuss. I want you to try that, and then we'll probably discuss it some other class. Maybe on Monday, if you don't have too many questions on the other problems. So first off, Coriolis's force, let me just repeat. If you have a rotating frame, you immediately have the centrifugal force, that's fine. But in addition, if the object has a velocity, a radial velocity, then there is also Coriolis's force. Okay. So this appears if the radial velocity is not zero.
Wait, shouldn't it be radial acceleration?
No. It depends on the motion. If the object displaces itself along the radius, that's when you have Coriolis's force. It's easy to understand why. So let's say, well, let me just draw another, just maybe smaller scale. So first, let's do this in the stationary frame. So in the let's say you painted the bowling ball and you'll roll it off. Then in the stationary frame, it looks like this. Right? But if the merry-go-round, this disc is spinning, then what happens? It looks like this. Does that make sense? The ball just kind of rolls backwards. So the trajectory of the ball in the curve, in the rotating frame, is curved. Okay? So this is the trace the rolling, the bowling ball will leave on the rotating disc. So this is the trajectory in the rotating frame. This is lab frame. And this is rotating frame. Now, since the trajectory is curved, that means the velocity vector was not constant. That means there was acceleration, and the acceleration was sideways. Okay? So it's perpendicular to the radius. So this is a very important thing to understand. So F inertia was also perpendicular to the velocity. So this is the Coriolis's force. It's different from centrifugal because centrifugal is always radial. This is perpendicular to both V and radius. So here. So it's a sideways force. Well, not both, but either one, right? Because velocity is parallel to the radius. So, Alan, does that address your concern?
Yeah.
Okay. Another way to understand that is basically is this. So you can think of this disk as a collection of thin rings. Every ring is rotating at a specific rate. So they all rotate at the same omega. But if you were to compute the velocity of each ring, that would be different, right? Velocity would go as omega times radius. So when you move from one ring to next, Can you see me okay or no?
You're sort of disappearing into the Penn State University background.
Let me try to fix that.
I just had like a clarification question regarding this force. So the Coriolis effect is why, toilets flush in opposite directions in Australia and the US, but why do they rotate in opposite directions on one plane?
Thank you for bringing this up. We'll debunk that myth in a few minutes.
Oh.
Let me just turn it off. So I was talking about those thin rings. Each of them is rotating with a fixed velocity, but the velocity changes from one ring to next. When you go from smaller ring to larger one, the velocity changes. So think about it. The ball was rolling sideways with some velocity, and then it moved to a ring that moves faster. Think of it as like in the airports, they have this moving, what do you call it? Thing on which you walk. Not escalator, but the horizontal thing. So in some places, there are two of them moving at different speed. So when you move from one speed to the next, it appears as if you have acceleration there. Okay? So the same happens when something rolls off radially, because you go from smaller speed ring to a larger speed ring. That's why your trajectory is curved. Does that make sense? I hope it does. So now you probably are wondering what it is mathematically. So first off, we know that it's directed backward compared to the acceleration, right? So I was describing the acceleration. The acceleration of the rings is with omega. You following? So there is this extra change in velocity as you move out. That acceleration is this way with omega. That means the force of inertia is backward. That's exactly what's curving the trajectory of the ball. Okay, folks, are you with me on this? I know it's a little bit tricky to keep track of everything, but this is how it comes about. So this force numerically equals mass times the sideways, let me just call it sideways. And this acceleration is actually equal, it's proportional to omega. The faster it spins, the greater the acceleration. It's proportional to the v. The faster you roll off, the more acceleration you experience. What's probably counterintuitive is this factor of 2. Okay, 2 omega times v. So v radial.
Could you like compute this using like the dv dt, where like v is the velocity of each ring at some radius?
Yes, you can pretty much do that.
Okay.
So why don't you try, by the way, by Monday, and if you guys have trouble with that, we'll do it together. Okay, everybody understands the setup with those rings? So yeah, let me pose it as a homework question. So consider thin rings with increasing sideways v. And derive a sideways. Okay, so try to do it by Monday, and Monday we'll discuss. Yeah, so again, the unexpected part is the factor of 2. The rest you can just get by units analysis. Okay. So this is Coriolis's force, and now let's talk about toilets. Actually, before talking about toilets, let me give you another question, which again may be a bit too challenging for now, but I want you to think about it, and we'll discuss it on Monday as well. But that should give you a sense of scale, folks, about Coriolis's force on Earth. So you know Earth is not spinning super fast, is it? It takes like 24 hours to complete one revolution. So here is an experiment. And of course, you folks in New York can do it very easily. Just find a skyscraper, something like, say, 100 meters tall. So if you drop a penny, just make sure there is no wind and things like that. So if you drop a penny from a skyscraper, naively, if the Earth was not spinning, you would expect it to fall straight down. But in reality, it doesn't. It drops at some distance off. Okay. Why does that happen? Who can explain?
Because of the Coriolis force, there's some like deflection.
Of course, there is Coriolis force. Yes. What kind of deflection?
Like
So let's understand. So if you look at Earth, so this is Earth. Spinning. And you got the skyscraper, not up to scale. The penny is falling down. So what's happening? It has some, however, small radial velocity toward the axis of rotation. Do you see that? There is a VR in here. It approaches the axis of rotation when it falls down. So if you go back here, this is like the opposite of this situation. You can imagine it worked precisely the same way, but opposite. Okay, so as it approaches, there will be Coriolis's force that deflect that velocity sideways. Okay, it will deflect it like into the page, right? So when it lands, it will be slightly off because of that. So let me give you some numbers here. Say H is 100 meters. The rest you can figure out. Well, G, assume G is 10. And figure out the rest. You need to find the delta X. And I can tell you the answer just, you know, if you have the right order of magnitude. 3 centimeters. Okay? A little bit over an inch. Okay, but, you know, check this, derive it. And put it in writing, in red. Home.
But do we need the degree of latitude?
It's a good point, yes. You can take New York's latitude, right?
All right.
Any other questions? Okay. Now, Andrew, let's go back to toilets. So you see that if the height is 100 meters, the deflection is 3 centimeters.
Right.
How tall? What's that?
I just said right.
Okay. Now, how tall is your toilet?
If I were to estimate, about maybe 40 centimeters.
Let's give it half a meter. Be generous.
Okay.
So, can you scale the answer accordingly?
So if the deflection is if the deflection is 3 centimeters for 100 meters, then at half a meter, you divide by 200, so 3/200ths. So 0.0015.
So, for toilet,
0.015, I think.
0.0.
15 centimeters. Oh, sorry. Oh, yeah. No, 3/2 is 1.5. Yeah. So 3 over 200, 0.015
That's
centimeters.
centimeters, right?
Yeah, centimeters.
Okay. So, or 0.015 millimeters.
Yeah, so very small.
0.1 millimeter, in fact, is the smallest scale that a human eye can if you
Perceive.
have two things separated by less than 1/10 of a millimeter, our eye cannot tell them apart. So it's at the borderline of that. Okay.
Mm-hmm.
So do you think that Coriolis force plays any significant role in your toilet?
Well, no, it can't.
Yeah, there are much more substantial factors that affect the direction of the whirl in your toilet.
Like fluid dynamics.
Yeah. So, but you had a legit question there, like why is it different in northern hemisphere versus southern hemisphere? Just think about it. So let's look at the Earth picture. If you're here, maybe it's not the best perspective to analyze this question. Maybe you can just think of the merry-go-round. When you look at things from above and from below, it's basically a similar issue to discrepancy that one person would say, the person looking from above would say counterclockwise, and the person looking from below would say clockwise. Make sense?
Yeah.
Now, hurricane is a different story, exactly, Leon. So hurricanes, they have a much larger scale and much larger velocities. So yes, the effect is much more dramatic. Oh, by the way, Andrew, we forgot to scale the velocity. We scaled the height. But yeah, you kind of assume that water starts from rest and then kind of drops, right, over the height of your toilet. If you make that assumption, then you just scale down the answer like you did. But with hurricanes, the velocities are more substantial, and the scale is also larger. So yes, hurricanes are affected by Coriolis force, and not just hurricanes, also rivers. Have you ever wondered why, like, say, in northern hemisphere, most of the rivers flow, I'm not saying all rivers, but the majority of rivers flow from north to south. And have you ever paid attention that like one bank is kind of steep and one is flat? Did that ever occur to you? Like think of Hudson River. Oops, my battery is about to die. So let me just state that, and you check if that's consistent with your experience. In the northern hemisphere, the right bank of the river, of a river, is tall, and the left one is flat. Why is that?
Is it because the Coriolis force pushes all the sediment to one side?
Well, it pushes the river, and the bank that the river is pushed into gets steep because it's constantly being, what do you call it? So basically remove the sand or whatever, dirt, and it constantly gets eaten by the water. The river moves, literally moves sideways. And the other bank is just flat. Okay? And exactly, that's Coriolis force. If you find the river that moves, say, not from north to south, but from south to north, it would be exactly the opposite. There are a few rivers that do that. Okay? There are rivers that flow like east to west, but not too many. The effect will be opposite in the southern hemisphere. That you can do just drawing rivers on this Earth diagram. Any other funny things about Coriolis force? So I wanted to quickly give you a neat trick that I actually wanted to spend more time on, but let me just start, and then maybe we'll continue some other time. And people from the spring, I think we did discuss it with you. You tell me if that rings a bell. The black box trick. Does that ring a bell? Okay, good. But let's make sure everybody's on the same page. So the black box trick. So this trick applies whenever you have two or more objects moving together. Okay. Applies when two more objects move together. So the simplest example is pretty much what we already discussed. When you have two boxes, but not on top of one another, just next to each other. So a small box and a large box. And let's say this is 1, this is 2, given M1 is say 6 kilograms, M2 is 4 kilograms, and there is an applied force. I'm not drawing it here because that's what you'll do, but this force is say 100 newtons. So I ask you to find the acceleration. Technically, I could ask you to find A1 and A2, and also the contact force, the normal force between the blocks. Say F12, which by Newton's third law is the same as F21. So this I want you to do at home, the second question. The first one, so first we need to argue that A1 equals A2. They move together, so their velocities and accelerations are the same at all times. So this is a consequence of this. And since they're equal, we can just call them A without the subscript. Now, technically, if you have zero intuition about this problem, what you'll do, you would write Newton's second law for the first block, for the second block, Newton's second law for the first, for the second block, and Newton's third law for the forces between them. Write down all those three equations. You will have three unknowns, the acceleration and the forces from 1 to 201, and you'll do the math and you'll find everything, okay? However, the black box trick says something very simple. It says that the common acceleration of, like, why is black box? We can actually put these guys in a black box and not care about the details of the inside. Just treat the whole thing as a whole. Again, officially we will call that a system, but for now we'll call it black box. So the acceleration of the system can be found by considering the total external force over the total mass. Now, what does it mean, total external force? Once you say there is a box, there is immediately a concept of internal versus external. Okay? So you add all the external forces. You don't care about the internal ones. For example, those forces 1, 2, and 2, 1, they are between the parts of the system, between the contents of the box. So you don't care about them. You only care about the forces from the outside. So the outside force is this, the F. There is also, of course, 2 forces of gravity, 2 normal forces, but as you can see, they like cancel each other out, so we don't need to worry about it. Okay. So the only external force is really this F. Okay. And the total mass is simply m1 plus m2. So the answer is easy, right? You get like 10 meters per second squared and so on. I want you to, okay, how many of you are familiar with the Atwood machine?
Is that the slope thing?
No, it's 2 masses on a pulley.
Oh,
Yeah.
oh yeah. There's a version of it where one of them is on a slope, but yeah.
But I
Oh,
haven't.
yeah. Of course, there are modifications of that, of course. But like the classic one is simply 2 masses on the pulley. Yeah, my battery is about to die, so the pen started behaving. I'll be right back, folks. If somebody can draw that for me while I'm getting my charger, I'll appreciate it. Okay, thank you, Alvin. This is exactly it. So what I want you to do, so again, typically, we'll actually discuss this problem in detail, I think, next time. But I want you to understand how to get this answer using the black box trick approach. So the spring people, did we do it in detail in the spring?
I think we might have.
Yeah, if you can look back in those notes. And, yeah, I don't mean you to do it like thoroughly, although of course you're welcome to. What I want you to get from this problem at home is to get this formula using the black box trick, using basically this formula. It's a funny thing you need to consider. So use black box trick to get the acceleration. Okay. And next time we'll do it rigorously. Okay, any questions? So that's where we'll start next time. Next time we'll just consider a bunch of different problems on black box track. Okay, if you don't have any questions, let's call it a day. Work on the homework. Feel free to start a discussion in the classroom if you get stuck somewhere, but just be specific. Like tell us what you've done and where exactly you got stuck. Okay. Yeah, thank you, Abhijit. Okay then. Have a great weekend. I'll see you on Monday.
All right, have a good weekend.
All right, thanks.
Bye.